Parallelism. It's from chapter 4 of Patterson and Hennessy Computer Organization and Design, as well as Appendix C, and chapter 3 of Computer Architecture Quantitative Approach book. So Appendix C has a lot of overlaps with chapter 4. Appendix C of this book has a lot of overlap in chapter 4 of the Computer Organization and Design. Okay? All right, so far we talked about this data path for the MIPS processor. Actually, we had jumps and a little bit more details, but that's not the point. You are familiar with the MIPS processor at this point, how it works, different steps involved in doing the process. Hopefully you know enough so we can start building on top of what we had and go for a little bit more advanced design. So this kind of processor that we talked about so far is called single cycle MIPS processor. The reason it's called single cycle is because the entire process from the beginning to the end happens in one cycle. So here we have the program counter going to the instruction memory, we fetch the instruction, then we decode the instruction. This is the decoding part. Now you know we have an entire module of decoding. We decode the instruction, we read the registers, and then we have the ALU operations, then we have the data memory, and then that last step was for some instructions, we write the results back to the register file. Okay, so there were these steps involved, and everything was happening in single cycle. Okay, so in one clock cycle, you do this entire process. So this sounds interesting because it's simple, right? And if you are familiar with the circuit, the combinational and sequential circuits, this can be implemented in this combinational way. You don't have to clock it. But there's a big problem here because when you have many different processes happening in one clock cycle, your clock cycle should be long enough such that you can get the data. We quickly covered the concept of the propagation delay in one of the modules I don't remember, which we were talking about full adder. I think it was module 5, integer arithmetic. I remember now. We talked about the propagation delay, and I mentioned when it's 32 bits, you have to calculate how long it takes to get the data on the output side. So you have to wait that much and then clock it again. Because if you clock it in the middle of the work, you're going to lose the data. Okay. So that means that for a single cycle processor, we have to have a long enough clock cycle such that we can get the data. We apply the input, we go through this process that I just explained, and we get the output, and then we can send the next instruction with the next clock. This means that clock frequency should be very low. Clock cycle time should be high, clock frequency is low. So we're talking about the difference between 100 megahertz, 10 megahertz to a few gigahertz. Okay. So the clock is always determined by the longest path. So you should remember that in the processor, we don't know what instruction they want to execute beforehand. So we always design for the worst case situation. It's the story that you said, so a lot of these guys actually do some computation, but we never use it. And the multiplexers choose what data we want to use. That's extra overhead. That's another type of overhead because beforehand, you don't know what kind of instruction you want to execute. So the design should support the worst case scenario. And in this case, we have to support the worst case in terms of the delay and latency instruction. Okay, so can you guess what instruction is the worst case instruction based on the things that we talked about? Explain it a little bit more. Worst case means how it takes longer, and what it really means is that it involves more blocks. Do you remember what instruction involved the most number of blocks in the MIPS processor? So if you have instruction memory, register defined ALU, data memory, and so on, and write back. So if you think about this entire process of reading the instruction, reading the registers, doing the ALU operation, using the memory, writing back the result in the register. You might not know. I mean, you know the instruction, but you never thought about it this way. Which one of these instructions does it cover?
Is it memwrite?
is membrane, which is stored, right?
Yeah.
So stored involves instruction memory. Everything involves instruction memory and register, read, okay? Then we have ALU to calculate the address. And then we have to store it in the data memory. Is it the longest one? It's the load word. And why the load word? Because load word has an extra step of writing back to. So store word, your task is done when you get to the data memory. In load word, you still need to read something from the data memory and store it back to the register file. So load word is the instruction that involves every block in the MIPS processor. Okay, but store word is the second person. There are some instructions that don't even need memory, so those are faster. But do we care about which ones are faster? No, because we don't know if we're going to have a load word or not. So our design should always, our clock cycle time should be designed based on the load word, as if all the instructions are load word. So that's one overhead, an extra overhead too. Okay. These are the reasons why we don't use a single cycle MIPS processor anymore. So when I was a graduate student, we actually designed a single cycle. I took the advanced computer architecture course, and who knows, maybe one day I offer the course here as well. So we designed the single cycle MIPS processor, and then we had the multi-cycle MIPS processor, which we're going to talk about today. And then you could easily see the compare them and see the differences in the latency, clock frequency, and so on. But in this class, we're going to use analytical models, and you should be able to analyze it even without actually having the hardware working for you. So this is where this chapter is called pipelining. So in the quantitative analysis book is instruction level parallelism, and I use that term. But in the computer organization book, it's called pipelining. So that's why I use the term pipelining. So now let's talk about pipelining. So this is a very well-known analogy that people use, and if you just Google pipeline, you see that picture is coming from computer organization book, and it's a laundry analogy. Okay, so let's say when we want to do the laundry, there are 4 steps involved: washing, drying, folding, and putting it in the closet. Okay, 4 steps. So one way of doing it, and let's say you have different piles of dirty clothes that we want to wash. Okay, so we have 4 piles of dirty clothes that we want to wash. So one way is that you get the first pile, you use that basket, you take it there, and go through the entire process, wash it, dry it, fold it, and put it in the closet, and then go back and use another one. Okay, if every step that we talked about takes half an hour, you need 2 hours to finish the first pile, which is task A. Then you need another 2 hours for the second one, another 2 hours for the third one, and another 2 hours for the fourth one. So right here, you spend 8 hours to do the laundry for 4 piles of dirty clothes, and now you're going to have clean clothes at the end in the closet. Okay? But now, these days, it's very intuitive for us that that's not the best way of doing it. Right? And that's mainly because we were born in a time that we have assembly lines, okay, and this goes back to 1913. A lot of people say Henry Ford was the inventor of that. It's controversial. People say it was there before it, but I don't care about that controversy. In 1910, 1920, it was a time that we built this assembly lines, and now it's very intuitive for us that it's not the best way to do this process this way, right? Because when your washing is done, your washer is free, so now you can use it. And while we're drying the first pile, you can wash the next one, right? So this is the way we can do our work today, right? We have the washer working for the first pile, we move it to the dryer, and now the washer is free, we use the second pile. Now, when we are folding the first one, we use a dryer for the second group, and then we can use the washer for the third one. Okay, so now if you look at it, after the first 2 hours, every half an hour, we're getting some clothes the clean clothes, right? Folded in the closet every half an hour. If you add this, you can do this process in 3.5 hours instead of at 8 hours. Okay. So this analogy is the entire idea behind pipelining. Okay. That's why we do pipelining. It's assembly line idea. It's an analogy. Why can't we do different processes? So now, before going there, just one question, because we're gonna talk about it later. What if one of these processes took more than half an hour? Okay, one of these steps needed more than half an hour. Then what should we do? How long would it take for them? Let's say just the drying part needs 1 hour. Okay. So for both cases, how long do you think it would take to finish the task? Just this one needs an hour. So I help you with this, and you give me the answer for the next one. If the dryer needed 1 hour, we need half an hour for this one, 1 hour, half an hour, half an hour. So this would have taken 2.5 hours every step, and then in 10 hours we could have finished the entire process. Okay, that's if we do everything in a sequence. How about this case here? The 10 hours for the one above, which is a single cycle. Now, if I wanted to do pipelining,
wouldn't it just add an extra 30 minutes to the whole thing because you just offset when you do the rest of the steps?
Yeah, so that's the first thing that comes to mind, right? So one step takes, second step in this case needs 1 hour, so we need an extra half an hour, and it's gonna be propagated through the entire process, right? It makes sense, but that's not exactly right. But I appreciate that because you're starting that. So now let's move it forward a little bit. Go by the end.
Add a half hour for each drying to offset.
We need to add the half hour to every step. Why is that?
Because the dryer will be full, so you can't dry.
You can't use it anyways. Yeah. So the dryer is your bottleneck here. So even if you finish a task in half an hour, you have to wait an extra half an hour to have a free dryer to use. Okay. So at the end, when you pipeline it, your steps is going to be 1 hour steps. So what it means is that it's going to take 4 hours to finish the first one, and after that we get one basket of clean clothes every 1 hour. So it's going to be 7 hours. Still, it's better. So it took 10 hours for this guy, and 7 hours for the pipelining to finish a task. But we always design the system for the worst case situation. So if you have one of these steps needing more than other steps involved, we should always design every step based on the worst case scenario. Okay, we're going to learn it a little bit better with more examples in the future. So this pipelining is a method that is called parallelism, but it's across the instruction level. Okay, so we're not actually using more resources. So later we talk about parallelism, we talk about having 2 ALUs, multiple ALUs, or so on. So here it's just an interesting approach to which some overheads that we're going to talk about. We can have instruction level parallelism. So your processor can run multiple instructions at the same time. If the stages are perfectly balanced, like the example that we showed in the previous slide, not the one I asked you, the one that is actually in the slide. If the stages are perfectly balanced, then the time per instruction on the pipeline processor is going to be equal to time between instructions of non-pipeline divided by n, where n is the number of stages, pipeline stages. Okay, so in that case we had 4 stages. So the time to finish a task was 2 hours. But then we noticed that we could get an output every half an hour. So 2 divided by 4 is half an hour. Okay? Because you have 4 stages. So it takes 2 hours to get one output. If you pipeline it, every half an hour you can get an output. Of course, you have an initial delay too. Okay? So now we have this laundry analogy in mind. Now let's talk about the MIPS processor. So first thing we need to do if we want to pipeline the processor, we need to find the stages. How many stages are involved in the MIPS processor? So we talked about different stages, but now we put a name for them. So you can use these stages for pipelining and so on. So the first step is the instruction fetch. In the instruction fetch step, we read the instruction, we send the PC to the instruction memory, and we read the instructions from the memory. At the same time, we do PC plus 4. Okay, so PC plus 4, which is what we did to go to the next instruction in the instruction memory, is done at the same time when we do fetching for the instruction. Okay. Then the next step is instruction decoding and register read. Okay, it's shown by ID, instruction decoding, but you should know that at the same time we read the registers too. We always read registers in MIPS processor, we know that already. Okay, these two steps we always do. Third step is execution. So we use ALU, it's called EX. We use ALU to execute the operation that we need in instruction. If it's a branch, we do a subtraction. If it's R type, we just do the R type instruction and so on. So execution is involved in the system. Okay. At the same time, we use this add and shift left 2 to calculate the branch target address. So PC plus 4 is calculated in an instruction fetch. In the execution step, we calculate the branch target address. Okay, so the output of this one is the branch target address, which is calculated in execution time. We're not using the same ALU, we have a separate adder for that. Okay? The next step is the memory access. It can be for a store board or load board. We access the memory to do something with it. Not all instructions need it, but we have to go through these steps anyways because we don't know what kind of instruction we want to run on the processor. Always design for the worst case situation. And the last step is write back, or WB, is when we write something back to the register if we need to. Store board, for example, doesn't use this step, but it goes through the step because we don't know what instruction we're executing. Okay, these are the stages now. So how can we create the pipeline? Okay. We can create pipeline by using registers. Okay. So now, before talking about registers and how we want to use it, let's go back to the laundry analogy and think about how we can do the pipelining. Okay. So if you want to use the same washer for cleaning two sets of clothes, you have to have something like a basket of some sort to store the clean, take out the clean clothes, put it in a basket, and put the dirty clothes in, right? Otherwise, there's a chance that you can mix them. If you just want to use, you don't want to use any baskets, you can just mix the dirty and clean clothes. But what you can always do is just take it out, put it in a basket, and put the next one in, and let's do the same thing in every step. So when you're doing drying, when you get the dry clothes out, you put in a basket, and then move what is coming out of the washer, which is already in the next in another basket, to the washer. So what we do is that we add a bunch of baskets in between every step, just to move around the cloth. Okay. So this concept of baskets for data is kind of like a memory, right? If you're just working with this, we need some kind of memory to store the data in every stage. Okay, but not any kind of memory. The reason we use registers, if you go back to, I don't remember what module was it, but we were talking about the register file. And I mentioned that registers use flip-flop to store every bit. And we mentioned that flip-flops are fast, but they also have a very interesting feature based on which we can write to the register flip-flop in the same clock cycle that we are reading from it. So in one clock cycle, we can read the data that we stored in the register, in the flip-flop, in the previous clock, while we are storing the data in this clock in it. Okay? How it works, the digital logic circuit can go back, it's just a bunch of transmission gates, and you can see how it actually works, but the only thing you need to know for now is that in a flip-flop, you can write a bit in it while you're reading the data that you stored in it in the previous clock cycle. So that's exactly what we need for pipelining. That's exactly the basket that we need when you want to take it out. We move the dirty clothes in, or clean clothes in, and then to the dryer. It's exactly the kind of basket that we need. So the technology is exactly the technology that we use in the register file. Flip-flops, okay? So every step, we have 5 stages. Going from one step to the next step, we have register file. We have 5 stages, not the register file, registers, pipeline registers. So we have 5 stages, we need 4 pipeline registers. Okay, the way we name them depends on where we place them. So for example, this is important because when we move forward, it can easily get confusing for you because then we're going to use some notations that really depends on the name of the registers. So try to have this in mind and how we name them because it's going to be confusing. But if you go step by step, it's going to be less confusing. So this register that we see here is called IFID because it's between instruction fetch and instruction decode. And we have the next register, which is IDEX, because it's between instruction decode and execution stage. And we have EXMEM, because it's between execution and memory. And then we have mem write back WB, because it's between mem and write back. Okay, it's very straightforward, nothing crazy. Okay, so now I want you guys to do something just for the fun of it. So every bit that we want to store in the register, we need 1 flip-flop for that. So if you think of it as a memory, what should be the capacity of this memory in terms of number of bits for the IFID register? So what we do here with registers are added to retain the values from one pipeline stage to another one. So we basically store the outputs of one pipeline stage in the registers, and the next clock, we use them as the input of the next stage. Okay? So the output of, every step is stored in the register, pipeline register. So can you tell me how many bits we need for the IFID registers? 64. That's right. Yeah. 64. 64 because we have the output of the instruction memory, which has 32 bits, and then we have the output of the PC plus 4, which is also 32 bits. So we need 64 bits here. How about this one? How many bits do we need for the IDEX register? Why do we need 128, sir?
Because we have like 4 into the...
Yeah, so this is simply moving from one pipeline state to another one. So one here, another one here, right? So another one here because we read the register, another one here because we read another register, and then we have the sign extended value. So 4 times 32 is 128. How many bits for X and mem? Andrew, how many bits?
97.
Let's see. So you have 32 for the first result, 1 for the 0-bit, 32 for the ALU result, and then 32 for read data 2.
Which makes it 97, right? Exactly right. 32 here, 32 here, 32 here, and 1 bit, which makes it 97. Okay? So 97 bits, and we need 64 bits for the mem to WB. Okay, so this is how much storage we need to add to the data path to support the pipelining. So right there we have the overhead, right? This adds some overhead, but it's absolutely worth it in terms of how much time we can save by pipelining. Okay. All right. So now let's have this example. We have an example that it provides this information about every instruction. We have the load word instruction that involves every step, 5 stages that we have. For instruction fetch, we need 200 picoseconds. For register read, we need 100 picoseconds. This is just an example, by the way, right? These numbers are not accurate numbers. ALU operation needs 200 picoseconds, memory access needs 200 picoseconds, and write back needs 100 picoseconds. For load board, we need 800 picoseconds to finish this instruction. And we need 700 picoseconds for store board, which is exactly, when Brandon said store board is really close to load board. So you need 700 picoseconds in this example. Then we have the R format instructions that don't need the memory access part, but they have the write back stage. They need 600 picoseconds based on these numbers that we have here. And then we have branch E code that doesn't need memory access and doesn't need write back, and it only consumes 500 picoseconds. Okay. So now the question is, we want to compare a single cycle MIPS processor with a 5-stage pipeline MIPS processor when they are executing 3 load word instructions. Okay, 3 load word instructions. So we want to see how long it takes to finish 3 load word instructions, 3 consecutive load word instructions. So this is the single cycle case. Okay, we always design for the worst case. This is load word, so I'm not even confusing you. I'm already using the instruction that takes the worst case, but if I add an add here, you would still design for the worst case, so it would have still been 800 picoseconds. Common mistake, if I put an add here, you don't have 800, 500, and so on, right? A single cycle is always designed for the worst case situation. So we have 3 instructions like this. Register 1, register 2, register 3. These are the indexes already. Only. And then we have 3 instructions, 800 picoseconds for load word, 800 picoseconds, and 800 picoseconds. So how many clock cycles do I have here? How many clock cycles do I need to finish this code? We need 3. So what is the clock cycle time? It's 800 picoseconds. And so what's the total execution time? 2400 picoseconds, right? Now if I do the pipelining, this is how it works. This is not a case of a perfectly balanced stage. We have stages that take longer than other stages, but we should always design it for the worst case situation, which is 200 picoseconds. Okay? If we had one stage that would have taken 300 picoseconds, laundry analogy again, then everything should have been designed for 300 picosecond delay. Now the worst case delay that we have here is 200 picoseconds, and this is how it works. We have instruction fetch, then we have the register read. This needs 100 picoseconds, but we have to wait 200 picoseconds anyways, because this is the worst case situation. For the next instruction, while we are running the ALU part, for the first instruction, the register file is free to be used for the second instruction, and also the instruction fetch. We are fetching the instruction for the third one. So instruction memory is used for the third instruction, register file for the second one, ALU for the first one. After this point, we're actually using the data path and it's not full capacity, but for this code, it's kind of like a full capacity of the memory. So we have the data access, ALU, register, data access, ALU, and so on to finish the task. Okay? So how many clock cycles do I have here? We have 7 clock cycles. 1, 2, 3, 4, 5, 6, 7. Every stage happens in 1 clock cycle. The moment that you add the registers need to be caught. Okay? So your clock is going to activate the register. It's going to register the input, the output of the previous stage, to the input of the next stage. Okay. So how many clock cycles do we have? We have 7. What is the clock cycle time here?
200 picoseconds.
It's 200 picoseconds, which makes the execution time equal to 1400 picoseconds. Okay? If you look at this, you can see that the first instruction needs 1000 picoseconds to finish. The first instruction for the single cycle needs 800 picoseconds to finish. So if we just have one instruction, the pipelining is hurting us. Okay? But after that point, every instruction can be executed in 200 picoseconds. Okay? Now, let's do some analysis here. We had this equation. If stages are perfectly balanced, the time per instruction on the pipeline processor is equal to the time between instructions in non-pipeline divided by n, right? So in this case, we have 5 stages, okay? So what we expected speed up was supposed to be 5, because we have 5 stages, and this is how we find this speed up. But what we really found was that the speed up, achieved speed up, is 2400 divided by 1400, which is equal to 1.7, right? So what is really happening here? Okay. The first problem here is we have to pay attention. This is the key word here. If the stages are perfectly balanced, okay, in that case, the stages are not perfectly balanced. We have to consider the worst case, okay? So the worst case needed 200 picoseconds, not 100 picoseconds. And the clock cycle time for single cycle is 800 picoseconds. And every 200 picoseconds we're getting one output, while in the single cycle case, every 800 picoseconds we're getting one output. So the end here should be 4. It's a 5-stage pipeline, but because it's not perfectly balanced, it's as if we have a 4-stage pipeline. Okay? If it's not perfectly balanced, we have to consider the worst case. So the speed up that we expect to get should be 4. Okay? But this is not even close to 4. It's 1.7. Okay? It's a little bit better. We don't expect 5. We're getting 4. But still, it's 1.7. It's not even close to 4. So what is really happening here? Can you tell me what is really happening here? What is the problem? We're expecting significantly more speed up with this pipeline. In this case, 4 times. Can you make a guess?
When you pipeline instructions, you have to wait at a minimum the worst case per each like instruction type. Like if it's instruction fetch or register, whichever has the greatest time, you have to wait that amount of time.
So that's a perfectly balanced case, right? So that's the case that we went to from 5 times to 4 times.
Right, if they were equal, then it's perfectly balanced.
But because they're not equal, we couldn't achieve the 5 times speed up.
Right.
But we still expect to achieve 4 times the speed up. But we're getting 1.7 in this example. 2400 divided by 1400. You already have the slide, so if you have it, don't look at it. Just make a guess. Mason, do you have any idea? Just make a guess, that's fine.
Could it be that with only these 3 instructions, you haven't given the pipeline enough time to really show the speed up?
That's exactly it. Yeah, that's exactly it. So if you only have 3 instructions, you don't even bother adding all these overheads and stuff, right? So it's not worth it. Well, now let's see if we had 1 million instructions, what would happen? Okay, if we had 1 million instructions, in the non-pipeline case, we have 1,800,000 picoseconds. If you multiply that, you get 800 million picoseconds. Okay, but in the pipeline case, you have 1,000 picoseconds for the first one, but after that one, you're getting one output every 200 picoseconds, right? So the first one is 1,000 picoseconds plus 999,999 multiplied by 200 picoseconds. So now if you do the multiplication, this is what you get. Now if you do the division, the number you're getting is 3.999984, which is fair to say it's really close to 4. Okay? So you need all these things is meaningful for larger codes. If you have like 10 lines of code that ends up being like 50 assembly instructions, I'm not really sure that you really want to have a pipeline processor. Okay? But you can easily get to thousands and millions of instructions with your code. Easily. Right? This is not a really difficult thing to do. In a loop, you have just a simple, fully connected net layer and a multi-layer conceptor and neural network. You can easily get millions of instructions. Okay, that's where pipelining matters. Okay, any questions? Okay, now
What about when instructions like are dependent on each other? You still have to wait.
Oh, you're going way ahead. Yeah. So this is like probably next week. We get to the dependencies and everything. Oh, maybe not next week. We just talk about it a little bit next session. But next week we go deeper into the data hazards, how to fix them, and so forth. The question is, if there is a dependency, then what you should do. That's absolutely a good question. When the input of one instruction depends on the output of another instruction. Just have that in mind. We'll talk about it in more details later. Okay. So now I want to talk about every step and what is happening in every step, the pipeline. Something that is really important is understanding these notations. Okay? This is when I said it's going to be very important in the exam, in the quiz. I think because you guys just care about the quiz. Not, but I'm gonna ask about like these notations. So you're gonna give the answer in notations, right? So just make sure that you learn it. So instruction fetch, and also when you see these guys in the books and everything, I'm hoping that every time you see a diagram like this, you can make sense of it, okay, in the future. So let's explain what it is. So in the instruction fetch step, and I'm giving you a load board case because load board includes everything. So this is just for load board. And we show the store word as well, but for now it's just load board. So instruction fetch, we read the instruction memory, okay, and we calculate PC plus 4, and store both of these guys in the instruction IFID register. So moving forward, I just don't say it completes IFID pipeline register. What happens here is that PC is the address, and this is how we show it. We have brackets here. PC is the address, and mempc is the content that is stored in the memory for that address. So we get the content, and we store it in ifid.ir. This is how we show it. So it means that this is in the IFID pipeline, and the register in the IFID pipeline is called IR, which is instruction itself. Okay, instruction register. So instruction code is read from the memory and is stored in the pipeline. The other thing is that we calculate PC plus 4 here, and we store PC plus 4 in another register called NPC, or the new program counter, in the IFID pipeline. Does that make sense? IFID pipeline, NPC is a register that is used to store PC plus 4. Okay, now let's go. Okay, and also this is something that we always use. When we highlight the right half of the block, it means that we are reading something from it. If we highlight the left half, it means they are writing something too. Okay, so we are reading something from the instruction memory, but we are writing to the pipeline. So the left half of the pipeline is highlighted, and the right half of the block. Okay, instruction memory is highlighted. Okay, so I already talked about it. Now let's go to the next step: instruction decoding. Okay, and reading the register. So the right side of the pipeline is activated because we want to read whatever was stored in it in the previous step. Okay, Now what we do, we get the RT part. So instruction had different fields, right? Instructions, depending on what type of instruction it is. This is an I-type instructions. We had RS, RT, and constant part, right? So RT is a field inside the register IR that is in the IFID pipeline. It's easily getting confusing, right? So IFID is the pipeline. We have IR already in that pipeline, and we get the RT part, just those bits, okay? And everything that we see here is giving us an address in the register file, which is shown by registers, for that specific register that you want to read. So you get to the RT field of the register that's in the pipeline. There you have 5, 6 bits. Those 6 bits are giving me an address, and that address is what I use to have access to the content of a specific register in the register file. That's reading the second source, because it's RT, the same story is for RS, right? RS is the first source. It doesn't matter. You RS field for the first source, RT field for the second source. Now, these contents, which are 32-bit contents, are stored in pipeline IDEX. Okay? IDEX is the pipeline that we store these results to. And that's why the right half of it is highlighted, because we're writing something to it. Okay? For the first content, we call it register A in that pipeline, so IDEX.A. And for the second register, the content of the second register, we call it IDEXB. So now we have A, which is 32 bits, B is 32 bits. They're both in the IDEX pipeline. IDEX pipeline by itself has 128 bits, we already know that. And this is going to be used later, but these are the contents of the registers that we get. So this is one of the things that happen. The second step is we get the immediate field from IR, which is the constant field, 16 bits. We sign extend it and store it in a register called immediate, IMM, in the IDEX pipeline. Okay? And the next thing is we just simply pass the program, the new program counter, to the next stage. It's going to be used later here to calculate the branch target address. So IFID NPC is moved to IDEX NPC. Okay? Might be a little bit confusing. You can watch the video later and follow it and see how it happens. Are you guys confused at all? Because I think it might be confusing, but maybe you're just smart enough to get it. But you can take a look at the video later if it's confusing. But it's pretty straightforward after you understand how it works. So now let's see the XMEM step. Here, this is the execution step. For the load board case, we want to add the register, first register, with the immediate part. Okay, to calculate the memory address. The ALU is using to calculate the memory address. So what we do is you just add IDEX immediate, which is already stored in here. It has 32 bits, with IDEX-A, which is the first register, and move the result in a register called ALU output in the XMEM. So ALU output is a register in the execution and memory pipeline. That's pretty much everything you do. Okay? At the same time, so this is the tricky part, what you really do is you also calculate the branch target address, and you also store the branch target address in the execution memory. For simplicity, we're not showing it here, we're just talking about the load board. Okay? But in a realistic case, this branch target address is calculated anyways. As you can see in these examples, we're not showing other multiplexers and the control unit. We're going to show it later, so it gets a little bit more complex, but for now we just remove the complexity and we're just focusing on load board. Okay? So ignore this part, but in real case, this part is actually executed as well. The branch target address is calculated and stored in a register in the execution memory pipeline. Okay? So now the last step is, that's not the last step, it's actually the memory step, which is where we access memory to load something from it. And what you really do here is that we have this address calculated in the execution stage and stored in the ALU output register that exists in the X memory pipeline. Okay, this is from previous step. So now I get this as an address, access the memory in that address, and store the content of that block in the memory to a register called load memory data, or LMD, in the memWB pipeline. We have the memWB pipeline. It has a register called LMD, which is the load memory data, in which we store the content of the specific block in the data memory, which is addressed through ALU output register that is stored in the execution memory. Okay? But this is what is happening in the memory stage. The last stage is the write back. So in the write back, we read the LMD, which is the content we read from the memory, and we just pay attention a little bit more here. So we have this, and we want to write it back to the register file. The address that we want to write back to is coming from the RT field of IFID. Okay? So IFID pipeline is sending me the address to the register that I want to write back to, and the content that I want to write back to is already stored in the LMD register in the memWB pipeline. Does that make sense? So this is the last step.
Won't the RT field be overwritten with the next instruction?
Okay, that's what I wanted to ask. Okay, I just give it a few seconds and then I answer that. Do you see a problem with that? With this, obviously you see a problem with that. But what do you think? Just think about it for a few seconds. What do you think is the problem with this instruction? This part of this step. So you should think of it as a pipeline processor, right? So when you're at this stage and you want to write something back to the register file, there are already instructions being executed in the pipeline. There are different steps of the pipeline though. Okay. So now if I use the IFID or RT, I'm looking at another instruction. So I'm executing, I want to write back the result of the instruction here, but the third instruction is already using IFID. So this that I'm getting, this information that I'm getting here, that is coming from this pipeline, is not the same target address for the instruction that I'm executing in the write back. It's a target address for 3-4 instructions after that. Okay? So I'm using another instruction's address to store back the result for another instruction. That's the problem, right? This is exactly where the problem happens. So how can I fix it? Now we know the problem, right? You understand the problem. Pipeline has different instructions. When I want to write it back, if I look at the IFID pipeline, this is working with different instruction, not the instruction that I fetched 4 cycles ago. That's the problem. How can I fix it? An easy way to fix it is send the address across the pipeline too. So if you want to write back, the target address that you want to write back to, you also send it through the pipeline. So instead of just sending it directly to the write register, you get this content and pass it through the pipeline with the instruction. And now when you want to write it back, this address is also coming from the write back stage. You get the address, but you don't send it to the register write, because we don't need to write the register at that stage. We don't even need that address. In a single cycle case, everything is happening in a single cycle. You don't really care about it. You just put the address there. It's going to be used later. Who cares? It's just everything is happening in one cycle. Here, you don't need the address until you want to write it back. Okay, so you might as well send it through the pipeline and send it back with the actual content that you want to write back in the register file. Okay, so now this is going to be a little bit different. First of all, we are adding the capacity of each of these registers, pipeline registers. So we add 32 bits here, not actually 32 bits, 6 bits. 6 bit here, another 6 bit here, another 6 bit here, 5 bits actually. 5 bits. So RS is past 5 was encoding, we know that. So we send 5 bits. We add 5 bits to each of these guys because the RT has 5 bits. We send it from one pipeline to another pipeline to the next pipeline and so on. So first of all, you have to add the capacity of the registers, of the pipeline registers, and also this instruction is going to change. Now, the LMD from the memWB is going to be stored in the register, but the RT is also coming from memWB pipeline. So it means that each of these pipelines here, they have ID, EX, IR, RT, EX, mem, IR, RT, memWB, IR, RT. So we have this in all of these pipelines. Okay. So that was the load word case. Let's work with these notations one more time. Now you have some idea about it. I'm going to quickly review it through another instruction that's called store word. Okay. Store word. So I want to make it a little bit faster this time, assuming that you have some idea in mind, some ideas about how this notation works. Okay, we have instruction fetch. We get the program counter, we get the address from the instruction memory, and we write it to the IR register in the IFID pipeline. At the same time, we calculate PC plus 4 and store it in the NPC register in the IFID pipeline. Okay, that's fetch. Decoding. We get the RS field in the IR register that is stored in the IFID, and we use that to have access to a register in the register file, this register file, and store it in a register called A, which is the first operand, and in the IDEX pipeline. We do the same thing for the second operand here. We have the RT field in the IR register that is in the IFID pipeline. We get that address, we go to the register file, we get the content out, we store it in a register called B, which is the second operand here, that is stored in the IDEX pipeline. Okay, that's the first step. The next step is that we get the constant field, immediate field, of the IR, which is stored in the IFID pipeline, and sign extend that and store it in a register called immediate or IMM in the IDEX pipeline. Okay. At the same time, we simply pass the NPC, which is exactly what we do when we are passing the RT field to. We keep doing the same thing here. So NPC, we're just passing this content from one pipeline to another pipeline. We have this register called new program counter from IFID that is stored in the IDEX, and we have the register called NPC. The third step is for calculating the address. Okay. So for calculating the address, we get the IDEX IMM, which is already sign extended. We add it with the first operand here, which is the IDEX EA. Sorry, A. So this first operand is A in the register. Is the register A in the IDEX pipeline, and we add it with the immediate. We calculate the result, we execute the result, and put the result back to, not put the result back, store the result in the ALE output register in the execution memory pipeline. Because it's the store word, at the same time, we get the B part. That's what we want to store, the second register. We get the second register from IDEX, which is B, from the register B, to another register B called in the X memory pipeline. This also happens in the load board case. We just didn't show it. This always happens. This is one of those cases that we do everything together and we let the multiplexers choose what they want to do with it. Okay, we don't have the multiplexers here. I'm kind of working as a multiplexer for you and just show the instruction that we actually need, the data that we actually need. But in reality, we move B to that register anyways, and later we decide whether we want to use it or not. Okay? So register B, which is the register that they want to write to the data memory, is also moved from the pipeline IDEX to pipeline EX mem. Okay, this is one of the differences between load board and store board. In the next step, we get the value of B from the execution memory pipeline and store it in the data memory. The address to the data memory is coming from the ALU output register that is stored in the execution memory pipeline. Okay, that's a step right back. We don't do anything in the write back, but we have to go through that stage anyways. Multiplexers control this process. Multiplexers doesn't let anything to be written back to the register file, but we still have to go through that step because the pipeline is designed for the worst case. Okay. So we have the load board store board. This is the table that is in the book. Actually, it's just cropped from the book. You can see every step. We have different stages, how the pipeline works. Now that you know the notations, you can go back and take a look at it and you can make sense of it. I don't expect you to memorize any of these things, but just for you to know. Just provide it here for your information. You can have R-type instructions, ALU instruction. As you can see, the first two steps for every instruction is the same exact steps. After that, things change depending on the instruction. Okay? And this information we already had too. Okay, so this is what is called the multi-cycle pipeline. If you look, so now we have a multi-cycle processor. If this is just a set of instruction, we're going to work with it later. I don't want to deal with it now. I just want to show you something before going there. So this is just, imagine we have these instructions. We want to execute these instructions using the multi-cycle processor, pipeline processor. And how it works is that in every clock, we send the instruction in. Okay, and then you can just follow based on, this is exactly what I want you guys to have some idea about. Based on these, highlighted parts, you can see what is actually being activated. So load board, right side of the memory, because we are reading something from the memory. This pipeline is active. Right side of the register file, because we are reading something from the register file. ALU is active. Right side of the data memory, because we are reading something from the data memory. And then the left side of the register file. For simplicity, that's something that we always do. So if I ask you to, for example, to put together a pipeline stage, it's okay to have these two registers here. Physically, we don't have two register files, but when you're showing the diagram, you just put a register file there. Okay. The reason you do it is because register file use registers. Registers use flip-flops. And in one clock cycle, you can read from the register and at the same time read to the register. Okay? And that's what is happening here. So if you look at, for example, this case, in this load board instruction and this load board instructions, we are using the register file at the same time, but one of them is being used to write something to it. The other one is just being used to read something from it. And that's something that we can do with register files. So for that reason, when you want to show the stage pipeline, although we don't have two registers, you put another register here just for the write back step. Okay, and that's how we show it. For subtraction, we don't use data memory, so it's just not highlighted. Do we have a store board case? We don't have a store board case, but if we had a store board, the left half would be highlighted. So these are the information you want to know. Something that I want to show you is that because we have five instructions in that example, and because we have 5-stage pipeline, in this clock, which is clock 5, we are using the full capacity of the processor. So every stage of the processor is actually executing something. You're doing something for some instruction. This is the ideal case for the pipeline processor. You want it to be designed in a way that you can always use it in full capacity. Every part, every stage is doing something. Can we always have a case like this? Absolutely not. Why? Because of what Brendan said, dependencies. Okay, this is a case that there's no dependencies. But if you, for example, you need the input, the output of this computation, this instruction, for the input of the next instruction, then you have to wait. Okay, this is something that we're going to cover in the next session. We start with that, we don't go that deep, but then we keep going deeper and deeper and add more details. Good for today. Any questions?